Hello and welcome to our video. My name is Hosni Fikri and I will be sharing you guys our solution regarding a beam problem using finite element method, and I will be discussing for the first part and then I will give to my friend Irfan Sharafi to cover the rest. I will be using this book as a reference, and the questions that we'll be discussing is under chapter 3 number 2. So if you guys have the book, you can turn to page 97. What we have here is a cantilever simply supported beam for the left hand side and an overhang beam on the right hand side. We have a uniformly distributed load of 12.5 for the first element and also a point load of downwards for the second element. So what the questions wants us to determine is the deflection and rotations at nodes 2 and 3, as well as the reaction forces at the supports and bending moment at node 2. Before we get started, I would like to refresh you guys about the degree of freedoms. For bar element, we only have one per node, which is the horizontal, and also for the beam element, we have two for each node, which is the vertical and also the rotation. This is the beam from the question. I would like to assign the degree of freedoms for each node. So in total we have 6 degree of freedoms. For the moment of inertia, I would like to change this quartic millimeter into quartic meter, and also this kilonewton per millimeter squared into kilonewton per meter squared, which is also known as kilopascal. Let's move on to stiffness matrix. So this is quite an easy part because you need only to substitute all the values here: the Young's modulus, the moment of inertia, and also the length of 5.2 meters. So this would be the values. Okay, next is load vectors. What we have here is uniformly distributed load. We need to change this into point load and moment. So this will be all the formulas. The last part is positive because the moment follows the direction of T4. And B1, B2, B3 we would have a value because of the support reactions. But for D4, we do not have a value because roller does not resist moment. Okay, the steps are basically the same. The only difference is the length because we are doing for the second element, which is 2.3 meters. And so this is the value that you guys will get. Load vectors. So we have no uniformly distributed load, but we do have a point load. Actually, this point load will be added in the global assembly of the load vectors. That's why we have 0 here. And this B3 is because the roller resists vertical direction.
Thank you, Husni. So, assemble the quadratic bus element 1 and element 2 to get the global stiffness matrix. The assembly of quadratic bar elements can be done as follows. Assemble global load vector. To emphasize the global reaction force, B11, B12, and B13 are expressed as B1, B2, and B3 respectively. Then calculate the deflection and rotation by using the formula of global stiffness matrix times by deflection equal to load vector. By imposing the essential boundary condition, the equation is reduced to D4, D5, and D6 only. Then, to know the deflection, rearrange the formula as deflection is equal to load vector multiplied by inverse of global stiffness matrix. So, we get the answer for the question 1. Next, for the second question, to get the reaction force, we use the formula reaction force equal to local stiffness matrix multiplied by deflection minus distribution load. So, for first element, the boundary is from D1 into D4. For the second element, the formula to get the reaction force is same, but the boundary is from D3 into D6. Then assemble the reaction force element 1 and reaction force element 2 to get the global reaction force for bar. So we get the answer for question 2. That's all from me and my partner Zul Husni. Thank you.